Hello, community. How do AI agents reason? So today we will jump from a chain of sort to a graph of sort. So let's start. Chain of sort, you notice. This is a linear sequences of sorts to come to the conclusion. What is graph of sorts? Well, you guessed it. It is an arbitrary graph with node and edges, where the nodes here are the sorts by our LLM, and the edges simply are the intellectual connectome for the reasoning structure. Now, AI agents process reasoning path in graph structures. So they follow here some path, and to find the right path is not an easy task. Now, this graph structures can be literally everything and every complexity. You can have a simple form of chain of sorts. You can go to the tree of sorts with some back way, which is, by the way, not efficient because the tree of sorts Achilles heel is its excessive reliance on LLM queries, at times necessitating hundreds of LLM queries just for one problem. And of course, you have multiple paths and you have to evaluate to rate the performance efficiency of a specific sequence of graph path leading to the correct result. So you see, oh yeah, there's something like, again, rating and evaluating here performances. So let's do 1 minute recap what happened until now before we jump into our topic. Easy. At first, since we talk about the reasoning of agent, what is an agent? An agent in the context of AI is an entity that can perceive its environment, maybe through vision language models, can make decisions, and can take action based on those perceptions of the environment and given a certain set of rules or policies. Isn't this great? We have this definition from Sutton here in this archive preprint from June 5th, 2022. And you know this. We have an agent that makes a decision and he decides to initiate an action. This action has an impact on the real world. The agent can observe here the impact in this real world. And we have here, if you want, a control cycle. And of course, we have a reward function. And you might say, hey, this is something I also have in reinforcement learning. And you just showed us in the last 3 videos how to do reinforcement learning. Well, what a coincidence. So here we go. Now, a year later, you notice that everything in reinforcement learning, and we have here a publication from the 12th of July. This is here from Canada, and on the 13th of July, we have here a publication from China, and both are on the impact on transformers in reinforcement learning. But nevertheless, you know that in my last videos, we were working with TRL with transformer reinforcement learning. So if you followed my last videos, you know exactly how to code the different steps using and utilizing the transformer architecture. So we are up to date. Never mind. Now, this simple definition by Sutton of what is an agent was elevated here by DeepMind. You see here July 20, 2023, the publication about continual reinforcement learning. And they had here the task to define in a mathematically precise definition what is an agent, what is an environment, what are histories, how you have an agent environment interface. It is simply a pair of countable set of actions and observation. Now the histories is relatively easy. This is just a set of sequences of action observation pairs given a specific time horizon. Then you have defined what is an environment to an agent in respect to the interface of the countable set of the action and the observation, We have here the function e-defined. And finally, we have here in definition 2.4, what is an agent with respect to the interface here of the countable set of the action and the observation. And we have here defined a function lambda. Now, if you want to dive into the mathematical construct, they have 33 mathematical theorems, mathematical lemmas with a proof. So if you appreciate or if you like this approach to agent, this is the publication by DeepMind for you. Great. Now, August 22, 2023, for me just a week ago, we had a new publication by Renmin University of China in Beijing. And they now focus here not only on autonomous agents that are maybe rule-based or something else that humans have written, but they say, hey, we want to focus here on large language model that are augmenting here our agent, where we have the LLMs as the main course, the main intelligence, if you want, for our agents. So as you can see, autonomous agent based on large language model is now here the hot topic. And you will remember in one of my last video when we talked about here the fine-tuning of the wizard coder 34 billion fit trainable parameter model, I told you that here when we have coding agents and we looked here at the Python coding LLM, we have in the core of an agent, we have here a code LLM. Or when we looked here as LLM as agent, when we have, for example, here the classical agent task of an API call, now we have an API LLM like Gorilla. I have a video on Gorilla where we see now that the complete complexity of API calls here, for example, to Hugging Face, to have access to more than thousands and thousands of machine learning models and data set you can use for LLMs. This here is now also an LLM and you get it. So we have this now all over the place, autonomous agents that are augmented by large language model or large vision language model or vision language action models. Great. Now, what the Chinese publication tells us, and this is nice, that our LLM-based autonomous agents are composed of 4 generative elements. We have a profiling module. Well, this just tells them, hey, what are you? I'm a storyteller, I am a coding LLM, whatever. Then we have a memory module for some short-time memories. We have natural language ICLs. We have some embeddings. We have some database structure that have external access to structures. We have a planning module. And they argue that, hey, when humans face a complex task, they break it down into simple subtasks, solve each subtask, and we come to the conclusion. And you notice this multi-path sort, you know here, chain of sort or tree of sort. And then you say, of course, if we have taken here the decision and the planning model comes to a conclusion and we have now broken up the task in subtask, we can now start action 1, action 2, action 3 to come here to the result. Beautiful. Yes, 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 you can imagine this. What is the most beautiful part here? Our LLM augmented autonomous AI agent can learn. Since they are interacting with the environment, we do not have to tell them anymore. They are like a little child, I don't know, stumbling around in the environment. And I showed you here in my video about AI robotics here, RT2 here, the robotics transformer applied with vision language model. This is exactly what they do. They interact with the environment, the robotic arm performs task, and given a vision transformer here, you have an immediate feedback so that the robot understands what leads to the correct action and which action should not be preferred for a specific outcome. Great. But it is not that here the Chinese publication was the first. No, we have Lilian Wang. And in June 2023, you have here Lil Slog. Highly recommend here this resource. And she was also talking about LLM-powered autonomous agent. And she also gave here an overview She had three components: the planning, the subgoal, and the decomposition. So the agent breaks down large tasks into smaller, manageable subgoals. You have reflection, refinement. You have a short-term memory, like in-context learning, ICL, prompt engineering, or you have long-term memory, where you have here memory about extended periods. You go to an external vector store, you go to an external database. And she says, given here the action component, there's a tool use. So for example, if you have some external API calls, she regards this as a tool use, which is great. Here is the HTTPS link. Have a look at Lil's blog. Now, she also breaks down here the first component, the planning, into two subtasks. So the task decomposition, this is what you know, chain of thought. So you see we are here on topic. And of course, self-reflection, where you know React that we used here, particular in the coding videos. So this was it. And now to the new stuff. We have two publications. Both publications say, hey, we go beyond the chain of thought reasoning algorithm, and we propose here graph of thought. And we have here the Shanghai University and the Wuhan University. And the second, this is from May 2023, and the second publication where they say we introduce also graph of thought. So it's the same labeling, graph of thoughts, from August 2023. And we have here the researchers from ETH Zurich. Great. Now, if you look at this, you think, hey, is it the same? No, it is completely different approach to the topic. So let's have a look. You remember when you watched this video here where we talked about OpenOrcher, that this was the move from the instruction tuning for our LLM, for the fine tuning where we have instruction-based tuning, to the explanation fine tuning. How we achieved this with Orcher, with OpenOrcher, the community did it, where we asked GPT-4 to explain here the way, the path of reasoning. So GPT-4 told us, hey, I argued step 1, step 2, step 3. So we recorded here the GPT-4 explanation of reasoning, and this served as a blueprint here, blue, nice, for our explanation fine-tuning of a particular LLM. Now, the next step is not so far away, because given here that GPT-4 showed us here the explanation, how it reasons, this is more or less what we're going to focus now. Now, let's have a look here at graph of thoughts, where we have, instead of a linear chain of thoughts or a defined tree structure with tree of thoughts, we have now the full flexibility. We construct our own graph structure from the simplest to the most complex structure, and we will see which structure and which approach is helpful for us. Now, you know chain of thought is a linear chain of thought. You know multiple chain of thoughts. Then you start here with 1, 2, or 3 ideas, and then you have an evaluation after some steps, and you say, okay, this is not helpful, this is not helpful, but this chain here, we follow this chain. And then beyond the tree of thought, we have now the graph of thoughts. You have in the right-hand corner the archive preprint link. And what you can do, and as I told you, this is a graph structure, you can do whatever you want in this graph structure. You can have here loops, a refinement. You can have, like in the tree of thought, some backtracking. You can define here specific paths. You can aggregate paths. You can re-enter here specific sequences of reasoning. So you have here complete freedom. However, talking about graphs, you know, I have 2 playlists on my YouTube channel about graphs. And I talk about graph data, how we build graphs, how we build computational graphs, how we have here, for example, in Python here, PyG. This is for torch geometric data, how we can calculate graphs. Yeah, a lot of coding about graphs. And we have knowledge graph with graph embeddings. And we have graph neural networks where we have different mechanisms. And you can go either with PyG or you go with Deep Graph Library, as here your Python-based library, exactly for calculating graph, to calculate message parsing, to calculate graph neural networks. Also, if you prefer here, this was in Keras, or you go with TensorFlow. And if you want to go the next mathematical level, I was talking about simplicial complexes. And then if you go beyond this, beyond graph neural network, but we just now apply here our graph knowledge to the current problem. Now, as I told you, we have here this, we propose graph of sort, the first one here from the Shanghai University, Wuhan University. They go straightforward more or less. So what they say, hey, we have maybe an image. And then we have some text and we construct here a graph of sort. So they come here to this sort graph, as they call it. But of course, they have to train a system. They have here to do some prediction. And the way they do it is, of course, straightforward. You have an image. So what you do? You take here a vision encoder, a vision transformer based encoder. You have text. Well, of course, either if you have the money for GPT-4, you use here an LLM, or you can go with a text encoder, like, I don't know, simple T5 or whatever you like. And then, and here comes now the graph theory that I just showed you, we have here the graph attention network. Now, this is something, if you're only operating with large language model and vision language model, you might not be familiar with, but in graph theory, this is one of the 3 most successful network architectures here in graph theory. So you have here an encoder, and then of course, you know, we have self-attention, but we have cross-attention. We fuse here together all the feature that we have in our mathematical representation in a space. And then you have a transformer decoder, and then you have it. So you see, you have to train a lot of models. So this is straightforward, clear, but I think with a lot of training. And they also say, hey, we also develop a novel extract clustering co-reference process to construct our sort graphs. It has something of a hierarchical clustering of graph, of subgraphs, but also important is the sentence, we are modeling the human's ability for leaps of sort. So they also rely a lot of the human augmentation. Given that this has such a high computational requirement, I would say, hey, you know what? There's another solution. Yes, there's a third paper because, you know, let's be a little bit more intellectually challenging. So we look here, August 20, 2023, algorithm of sorts. We have here Virginia Tech and, one from Microsoft, and they say also, so surpassing the chain of sort, we now here with LLM models, of course, we use here the reasoning capacities of LLM. So again, we go here with LLM-augmented autonomous agent. We propose a new algorithm of sorts. Well, isn't that great? And they have a very clear visualization. So you have the normal standard prompting. You notice you have a question and you get a direct response. Or you have a chain of sort where you as a user have your input, then you have here the assistant, you have here an ICL, and the model more or less gives you here the result based on the example you provided in your prompt. And now with this new algorithm of sort, if for example this here is an example for the game of 24, what you do, you now define the complete sequence of all possible solutions in your ICL. Now, I think this is quite some data. So let's see what they say. This AOT in context example, this is our in context learning prompt. Is it distinctive from here the chain of thought? Yeah, it has much more examples if you want. Highlights by the markers 1 and 3 as first operator, guiding here the subtree exploration. So what does this mean? If we have a graph structure and we have one subtree, two subtree, or multiple subtree, we have explicitly for the concrete task to write out all and each theoretical possibility of each and every subtree that is possible in this graph structure. And they say, hey, for clarity, only a single in-context example is displayed. And this is what I have here with the green background, with a focus on the third subtree exploration. So given here one specific user input for the game of 24, you have here the first subtree, all possibilities. Then here you have the second subtree with all possibilities. Here you have the third subtree with all possibilities. But you see this for a simple ICL, the amount that you as a human have to invest to find here all possible solutions about all possible subtrees. I mean, this is a rather easy example. If you go to a more complex example and you do not have an abstract solution path, but you have an explicitly defined with numerical examples that are absolutely corresponding to the user input. This is a lot of work. Let's put it in this way. This is a lot of work. So I would say, hey, let's move on. And yes, you saw it. The graph of sorts here by ETH Zurich. Let's have a look here at the third paper where we move from the chain of sorts to a higher complexity. They also call it graph of sorts. So what is it? Now, they say that their GoT architecture has more or less 4 elements. We have a prompter who prepares the message for the LLM. We have a parser that extracts the information from the response from the LLM. So we know what this is. Then remember, in reinforcement learning, we have to evaluate, we have to score this somehow. When we have research reinforcement learning from human feedback, we can score here the quality of the answer. This is more or less exactly the same. So this assesses the LLM replies for accuracy and relevance for specific tasks, confirms if the LLM sorts, these are our notes, meets the correctness conditions, and assigns a score. Let's say 1 for, yeah, this is absolutely the way to go. 0, I have no idea what the machine is replying. So you have here a scoring mechanism. And then this is now the most important part. Since you have an input, you have an output, you evaluate the output, but now you have to define here the complete reasoning process. And the authors of this preprint argue we have a controller. And this controller manages the entire reasoning process and its progression. So strategically chooses sorts from here a specific system, determines the transformation, and manages the interaction around with the LLM based on the GO. And you might say, great, what is he talking about? Now, this controller has 2 units, and the most important unit is the graph of operations, GO. Now, this is, and now careful, a user-defined preset structure, detailing the decomposition and the execution plan for a task, dictating, really absolutely dictating here the transformation of the way the path forward for the LLM, the way it is thinking, for the LLM sorts. So, you remember what I showed you before, where we had to explicitly, with all the numbers here in the example, now we have here a preset structure, but a generic structure. And then we have, if you want, you have this GO, you just have here a register where all the specific values are registered within. So if you want, this stores here simply all the variables of your GO, and this is called a graph reasoning state. So whenever one of the values changes, the state of the system changes here. And this is a real-time structure storing the ongoing LLM reasoning process parameters. Great. Now, I ask here GPT-4, this is my GPT-4 system, it's a screenshot, to give me a simple example. Because honestly, reading this in the train, I was a little bit overwhelmed. And I said, okay, again, what is this? So here we go, a simple example. And GPT-4 was really helpful, and maybe it is completely wrong. You have to decide. Scenario is planet classification, based on the LLM responses. So imagine you are building an AI system to classify planets based on their attributes, using ChatGPT. So what is the main task? You classify a planet here in the simplest possible, you have a binary decision. I can live there, I cannot live there. Habitable, non-habitable. Based on the physical, chemical attributes, the diameter of the planet, the distance from the sun, whatever. Water presence, and so on. And then we have here our GO, our graph of operations. And let's say, simplest case, we have 3 nodes. So the first node simply asks the distance of the sun and converts here the response about the distance into a standardized unit. Astronomical units, great. Then we ask about the planet atmosphere decomposition. And the transformation is simply categorize the atmosphere. Can I breathe it or not? And then the third node is about, is there water or not, sufficient or insufficient for life-based. Beautiful. Now, before classifying the planet, the system should have information from all the 3 nodes. Now, it is not about doing this for a correct answer. I just want to understand the reasoning structure that we can build. I know we can build graphs that are extremely complicated, but how is the interplay here in this specific model? So execution plan is clear. Execute node 1. If the distance here of this planet that we define is in the Goldilocks zone, so we will have fluid water, execute node 2. And if the atmospheric conditions are okay for life, execute node 3. And then we can have a classification of the planet. So the easiest graph structure you can think of, node 1, 2, 3, and you need an input from node 1, 2, 3. As I told you, we take this example here, the graph operations here, and now we add the graph reasoning state, the GRS. I record this in 4K, so on a 4K screen, this is crystal clear. GRS starts at an empty structure. After executing node 1, GRS updates simply here the response about the distance then in astronomical units. Following node 2, GRS updates here response about the planet atmospherical conditions, categorize the atmosphere, and it goes on. So you see, this is the interplay of a GOO and a GRS. If you want, here you define the complete complexity, the abstract complexity of the complete system. And here you just record whenever we get new information or you have an update of any of the system parameters. So for me, this is the way forward. Great. Now, this was a very simple example. Let's do an example that is a touch more complicated. So again, I needed GPT-4. I was sitting in a train and I said, hey, G, I need some help. So we have the same task, planet classification with graph of sort system. We define the task. Classify a planet into different types, and I will show you 4 types based on the list of features that I provide you. And I will show you the features in a second. So we have a simple setup for this task. We have an input and an output. And you might say, hey, wow, clever, huh? Yes, I know. In the input, I give you here a comprehensive list of the features, like diameter of this planet, the distance from the central star of this planet, the atmospheric composition, and whatever we need. And then, of course, I need an LLM that has been pre-trained, fine-tuned, reinforcement learning by human feedback on the topic of analyzing and providing planetary classification task. So I need an LLM that knows all the planet in the system, all the exoplanet in our galaxy. I need here an LLM for astrophysics. You got it. And then what I want here as a result. And I want that the system classifies here, given my input data. Is it a terrestrial planet? Is it a gas giant? Is it an ice giant? Or is it a dwarf planet? This is it. This is the task. This is the setup. So how is now the GoT system? How we build it? How is the interplay? Let's have a very easy example. As I told you, we have the prompter. This is a module that crafts here a query that we will send to our LLM. So this is my task as a user, more or less, to do this. So simple say, hey, define a generate initial prompt based on the feature. And the prompt is simple as it can be. Hey, give me a planet with the diameter of 5,000 kilometers, distance from a star of 2 astronomical units, an atmosphere composed of CO2, oxygen, whatever, classify its type, and return the prompt. So this is here my function, beautiful. And to make it a touch more complicated, because we want to see the graph structure of the reasoning, I say, by the way, let me here generate here a prompt, a user feedback. So I say here, consider the feedback that a planet is more similar to, I don't know, Uranus or Venus. Can you reclassify the planet? So you see I have a control loop. Right, this was the prompter. Now, then, you know, as the authors defined, we have a parser. And this module extracts some meaningful data from the response we get back from the LLM after we send this to the LLM. And now the parser response here, for simplicity, I assume that the LLM returns here a clear type and says, hey, this is it. So we have a response from our LLM that is clear. Then, as I told you, we have to score it and validate it because there are different multiple paths. And we need, hey, this has a high probability to be successful. This has a low probability given a multitude of path sequences forward. Not an easy task, by the way, but we are here in the simplest example possible. So we say here function score the response here, given the feature and the response. And here we simply employ some heuristic or some model to assign a score. You can define the model, but let's just say 85% sure. So we say, hey, our LLM, let's say GPT-4 or ChatGPT, whatever you have, say, hey, the answer is 85% correct that I've given you here, given the input parameter you provided me in the prompt. Great. So I have now a score, and this is important for the path of our reasoning. And then to GoT and incorporate user insight. So I have here an optional feedback module for the user, because I want to put my hands into the system and say, hey, wait a minute, what if I modify this? So I have an error bar that's a little bit more than I've given you. So I have here my user feedback, but never mind, this is not essential. And now we come to the most important part, the controller. Control oversees the entire reasoning process of GoT and its progression. So here we will use now all the functions that I just defined. And we have here the sequence how the system should argue. Great. So we have an initial prompt I just showed you. Then we query the LLM. We get a response. We score the response, as I told you, 85%. And then, yes, I am a user and I have a feedback and I say, I don't know, can I modify something? So I have a feedback loop and I say for the feedback, I have 3 iterations. So I limit here the iterations for simplicity to 3. But you see, again, I have here the follow-up prompt, here again, our LLM. So I can go in multiple loops, or I can reach out after 2, whatever you define. You as a user define here the GOO. And then you get a result. Great. Yeah, of course, every iteration, the data changes, so you record everything. The graph reasoning state dynamically keeps track of the input features the current classification status, the confidence score that we get, the iterations that have been conducted, the feedback from the user, everything is registered. Great, because the system has to learn from its history. And then comes the moment we all have been waiting for. We put all the components to work. And here, GPT-4 words, hey, features are, this is the diameter, this is the distance from the central star, this is here the atmospheric decomposition. These are my input parameters, and given my GOO here of GOT, I say now, hey, call the controller with all my features I just given you. And then here, our controller here, our simplest function possible, gives us here then a prediction. So by following this reasoning process that we imprinted here, the system achieves the classification and only utilizes the capability of the LLM, but it also benefits from the domain expertise of my personality, my goodness, poor system, ensuring a more accurate and a more refined outcome. Isn't this beautiful? So you see, it is much simpler than having here each and every subtree defined in each and every numerical value. I generate here a generic augmentation pattern. But I, as a human, I have to know about what makes sense to argue and not to argue, and to build up here my structure with loops and iteration and whatever you can think of in graph theory, build it. But for one particular problem, you have to build one particular abstract GOO. Okay, I hope this becomes now a little bit more clear, because if you read only the paper, I can tell you it is not that easy. Right. Now, talking again about the flow structure, I just ask here GPT-4 to give here another presentation that you can absolutely clearly see here the flow. So at first, as I told you, GOO, static layout, how the operations interact and depend on each other. Now, a planet classification system, it is simple. I have a start node, initial prompting, LLM query, I get the query back, I parse it, I score it, I validate it, I have maybe a user feedback. User feedback leads to some iterative refinement if a feedback indicates it's needed. I have another query, 2-3 times, and then I have a final classification output. So this is here, if you want, a very simple sequence. Then, graph reasoning stage, this is just recording all our changing values. You have the controller. Yes. Again, prompter, parser, scoring, validation, the feedback, and the execution. So everything is here in a control flow, detailed listing, if you want to check this. Now, you know me. If we learn something, I get ideas. I get some brilliant ideas, and maybe sometimes I get ideas. GPT-4 tells me, this is not the way to go, as in this example. So I said, hey, this GOO, this graph of operation structure, so this real abstract of a reasoning construct I have to apply for a very specific problem. Can I do this somehow automated? And GPT-4 comes back and says, no, buddy, no. In the example provided, the graph of operation was not created by the LLM itself. Well, of course, it was in this demo. But the GOO, as described in the official paper, would be designed by a human. Someone like you, who understands the problem domain and has a clear idea of reasoning, of the reasoning flow required to solve the problem. So you see here, the human input is here extremely important, that you have a domain expert for a particular problem in a particular domain. But what would happen if this human forgets maybe some possible theoretical solution? So, me, I asked GPT-4, I went at a little discussion with GPT-4, and so GPT-4 then agreed. Okay, however, an interesting concept to ponder upon is the idea of meta-learning or self-improvement, where advanced AI systems, GPT-5, might potentially suggest, yeah, GPT-4 is a little bit theoretical, will even design their own geostructure. So here we have it. If we have enough training data, so we need a vast number of interaction and learning here from diverse tasks in multiple domains and multiple complex graph structures. But you know, we have the mathematical graph theory. So I can say, hey, construct the first 1000 graphs for a particular problem given I want to achieve a specific outcome. But then we have here to train the model on this till another AI system is able to build here adequate and successful geostructures. So you get an idea where maybe in the next month, or maybe it's already here in the pipeline with Google or Microsoft or whatever, these geostructures and this reasoning pattern that go beyond chain of thought, that go beyond multimodal chain of thought, that go far beyond tree of thought. Here, this freely definable graph of thought structures. I think this is challenging, and the beauty is that here we have the mathematical construct of graph theory really contributing massively here to our AI system regarding reasoning when we have LLM-augmented autonomous agents. This is it for today. I hope it was a little bit informative. I hope it was a little bit challenging today, and it would be great to see you in my next video.